Okay. Nope. Except now we don't have video. Solve one problem, break the other. Okay. All right. Okay, I think I probably wrote this. Ooh, definitely have an edited version of that where I took that period out. Hopefully, I didn't. I don't think I changed anything else. I think recall from calculus, or even we've already said this before. I probably wrote this before I had locked in some of the things earlier in this unit. But when your function has a denominator that equals 0, you may have an asymptote, right? We've even gone to the fact where it's kind of like it has to do then with the numerator. If you're a non-zero over 0, then you do have an asymptote. That's kind of what we're going to see here. If it's 0 over 0, you may have an asymptote. In most of our cases, we've actually, it's kind of cleared out and we've figured out the answer, but it's not a guarantee that when you're 0 over 0 that you won't get an asymptote. Okay, so let's kind of formalize this. We're going to kind of use some of the stuff we did in factor and cancel, and we'll formalize it. So let's get this thing factored. We have this function f of x. I don't want to put it. Yeah, I can put an equal sign here as long as I don't cancel anything. So on the top, I get x what? Plus 3 minus 2. I agree. And even easier on the bottom, I get, yep, -2, -1. I'm going to write them. Okay. The function that I have written on the function that was written on the paper equals the function on the right. If I cross out those x minus 2s, I am making a linkage error because the function with those x minus 2s works for x equals 2. But if you plug in 2 into this, you'll get 0. So those functions are equal. I can't cancel unless I'm using limit notation. So what's the domain of f? Which values, it's actually easier to ask the other question, which values can't I plug into f? Yeah, 1 and 2. 1's going to make that first factor in the denominator 0. 2 is going to make that second factor in the denominator 0. So if our cumbersome notation for domain means we can go from -infinity all the way up until 1, but we can't use it. Then we can go from 1 to 2, but we can't use that either. But then we can use any number after 2. So the next thing we're going to do is I'm going to open up Desmos and we are going to sketch a graph of this. Blank Desmos. Alrighty. All right, so we have x squared plus x minus 6, and I used capital X somehow. All right, and we got that over x squared minus 3x plus 2. Except that's a 3. There we go. All right. So our graph actually looks pretty simple to draw. Is that correct, right? Plus x minus 6 minus 3x plus 2. Yeah, we're good. Our graph is pretty simple to draw because it's just kind of two curves. There is an asymptote, it would appear, if my pop-up wasn't in the way. If I even zoom out a little more, that asymptote is on the line x equals 1. So only one of those two values not in the domain gave me an asymptote. If I take and hover my cursor closer to x equals 2, I should see that when I get it to right on 2, my dot pops open and Desmos says, you know what, it sure looks like there's something here. I'm not going to tell you what that is. That something is the limit. But I'm not telling you, and I'm just going to say undefined, right? So let's make our graph look like that. Let's put an asymptote on x equals 1. that dot, let's kind of try to, we should be able to eyeball it. It should be a whole number. Sure looks like that dot is on. We're actually kind of doing limit here. If I can just get my finger to work. Bringing it closer and closer to x equals 2. I've got to go left to go smaller, and it's throwing my brain off. Yeah. Sure looks like as I'm getting close to 2, I'm getting close to 5, right? Yeah. I could just do it. Yeah, because it's coming down. When I pass 5, I'm lower than, when I pass 2, I'm lower than 5. When I'm before 2, I'm higher than 5. So that dot is at 2, 5. And we have something. It does also look like we have a horizontal asymptote of 1. So, shoom, shoom, and then shoom. It's so much easier to write on paper. Should be coming from the 1. There we go. We'll take it. Too low. That's not big. Yours looks better than mine, I'm sure. All right. So which of those x values not in the domain produced an asymptote and which do not, and why? That's kind of, this is how it works. We had an asymptote at x equals 1. So x equals 1, asymptote. And that's because we couldn't completely cancel. Oh, I'm sorry. I still have the graph up. My bad. X equals 1 is an asymptote. And that's because we couldn't cancel that out of the denominator. We couldn't cancel. But x equals 2 gave us a whole. And that's because we can cancel x minus 2 out of the denominator. One of the things that we do in calculus is we try to look at functions and decide what their graphs look like without actually seeing the graphs. So that's kind of why we're answering these questions. I don't need this graph to know those two pieces of information because this is how it works. If you're going to be able to cancel out the problem from your denominator, your limit will exist, and that's going to give you a graph with a hole there. And that you now have the coordinates of that hole, the x value you're taking the limit at, the result. That 5 does come from taking those x minus 2's away and plugging 2 into what's left. 2 plus 3 is 5. 2 minus 1 is 1. 5 divided by 1 is 5. So that is kind of a big picture of how this works. Okay. So now, the other thing we're going to have to do in this section is we're going to have to evaluate limits where our answers are going to be infinity. But again, we're not going to have the graph. So we're going to put those answers down here using the graph, and then we're going to see how we would do that without having the graph. So as x goes to 1 from the left, the limit is negative infinity. From the right, it's positive infinity. And overall, we would write does not exist, right? So this is going to be negative infinity from the left, positive infinity from the right. Best we can do for the end one is does not exist. And we've already said it, the limit as x approaches 2 of f of x is 5. And I talked about how we would get it without writing it all out. But it would basically be after you canceled the x minus 2's, plug in the 2 into what's left, and you're good, you'll have that limit. Okay. So what we're going to do is make a sign chart. These really come down to making a sign chart. When you go to make your sign chart, you're going to take the factored form of this problem, and you're going to look at all of the zeros, everything that makes any one of these pieces, numerator or denominator, 0. And we have three different values there. We have -3, and then the two values that weren't in our domain. So there might be an extra number we have to show in our sign chart that is in our domain. -3 wasn't a problem. It's just the value that makes the function 0. And hey, I actually didn't do too bad of a job of getting that there. It's almost 0. So we're going to make a number line. We're going to label that number line with what it's a number line for. So this is f of x from above. I'm going to put those three numbers in order. So the first one is -3, the next one is 1, and the next one is 2. I am going to, so I can zoom in better, rewrite f of x over here, just so that I can have it on my screen. You don't need to write it because you can see it on your paper. And then what you have to do is you have to go through each one of those pieces and decide where it's positive and where it's negative. So I'm going to start with the x plus 3. This is actually easy, and you can kind of get into autopilot on this. Just be careful if you don't need to. Anytime you have x plus or x minus a number, it's always the same. X plus 3 belongs to the -3 here. When you plug in numbers smaller than that number, you get negative results, right? Plug a -4 in here, this whole thing is negative. Plug a -10 in here, this whole thing is positive. But on the other side, you start getting positive things. If I plug -2 in here, now I'm positive. If I plug 100 in here, yeah, I'm positive. So as long as you're an x plus or an x minus, that thing's contribution to the sign chart should be negative before you hit the number and then positive after it. So that x plus 3 is negative before -3 and positive after it. I'll move on to x minus 2, and that shows up twice. So I need to use it twice. X minus 2 works the same way. Its number is 2. If you plug something smaller than 2 in, you're going to get a negative result. If you plug something bigger than 2 in, you're going to get a positive result. So this, same idea, but I'm going to make the change at the negatives, or sorry, at the 2, negative, positive, sorry, negative, negative. I'm actually going to make the change at the 2. Negative, 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 positive. My brain was already ahead of me. And then I'm going to repeat those down in the bottom because I have an x minus 2 in my denominator as well. And then last but not least, I'll circle around to my x minus 1. And same deal. 1's its number. It's going to be negative before 1 and positive after it. So I'll do a negative, a positive, and a positive. So now what I have to do, what this is telling me is, if I pick a value from any section of this sign chart, so if I pick a number smaller than -3 and actually plugged it into my function would end up doing a negative times a negative in the numerator, and then a negative and a negative in the denominator. So that is true for any number smaller than -3. So that means that I know the overall sign of every single value of this function to the left of -3. And if I multiply and divide 4 negatives, my overall sign is going to be positive. And for a different color. I don't have black. Black. All right. Black. After the -3, I have 3 negatives and a positive. So now I'm going to end up negative. Between 1 and 2, I have 2 positives and 2 negatives. So my overall result when I multiply and divide will be positive. And after 2, I will also be positive. From this, I can determine which signs my infinities will have if I know that there needs to be an infinity there. As I approach 1 from the left, all of my function values, according to the sign chart, are negative, right? So the limit as x approaches -1 from the left is negative infinity. As I approach 1 from the right, all of my values are positive, that's how I know that it's positive infinity. That's how we do these problems without having the graph in front of us. Yep. One extra thing here. So you might catch this. What I've done isn't wrong. The fact that x minus 2 canceled, actually, because we ended up with a hole and not an asymptote, this actually has no bearing on the sign chart. If I took all those greens, minuses, and pluses away, they'd be the same result, because here you added 2 minuses that cancel each other out. Here, 2 minuses that cancel each other out. Here, 2 minuses that cancel each other out. And here, 2 pluses that, cancel each other out, or just plus to begin with, don't affect the sign. So canceling factors don't really affect the sign chart. I think this would have been weird for me to say in the beginning, just do it with these factors. But now that we've seen the whole sign chart, you don't need to do these factors. You just need to do the ones that don't cancel. That's enough to make your sign chart. So you just need blue and purple. And I will underline purple here since I didn't before. Okay. Questions on that? Yeah. And right, for the same reason, right, the 2 doesn't matter either. Yes, for that exact same, yeah, right along the same thing, that 2 does not need to go in the sign chart. I'm not sure if that happens as much. It was just that I wanted an example with one of each, a hole and an asymptote. So I think a lot of times in these problems, that doesn't happen as much. Okay. Actually, yeah, no, I guess, yeah. All right. Yeah, so. Okay, so let's do at least 2 examples. Yeah, this isn't too bad. So this is a repeat, right? We have another polynomial fraction, rational function. The top is already factored for us as x minus 3. No surprise, we get an x minus 3 in the denominator, and the number that goes with that will be plus 1. Those 2 functions are equal. So not worrying about the canceling factors, what we can do here is make a sign chart. The only number that we need on that sign chart is, yeah, but we just said, do we need the 3? Yeah, yep. No, so that is good. No, I was trying to think ahead on that one, but yeah, this will happen a lot. You do not need the 3 on the sign chart. So things that cancel don't need to be there. And it's just x plus 1. The way this works is you are negative in front of it and positive after it. The only time that relationship will fall apart is if you have like a factor that's 1 minus x. That's why I keep saying it that way. So it's not like a guarantee that you're always writing minus plus. But since it's x plus or x minus, it's always going to be minus plus. This would just be the reverse. Numbers smaller than 1 will keep you positive, and bigger than 1 would make you negative. All right. So we have an asymptote at x equals 1. We know that because if you plug 1 into this function, you'll get negative 2 in the numerator. And if you plug 1 in the denominator, you could do the polynomial algebra, but just the simple fact that there's an x plus 1 factor, that guarantees you're going to get a 0 in the denominator. So you're in a non-zero over 0 situation. That guarantees that your left and right limits are either positive or negative infinity. The sign chart tells us which ones they are. As we go from 1 to the right, are we going to get positive or negative infinity? What does the sign chart tells us? Positive, yep. On the other hand, 1 to the left, we're going to get negative. And our overall is going to be does not exist, yep. On the other hand, the limit as x approaches 3 is the limit as x approaches 3 of the factored version. Now that I've got limits on both sides there, I'm allowed to cancel those x minus 3s. And that gives me 1 to placehold in my numerator, 3 plus 1, which is 1/4. My next questions on that? Makes sense. It's just this extra piece we have to do. We've kind of talked about all of this stuff before. When you're a non-zero over zero, that guarantees an asymptote. So now we're going to know to make the sign chart based on the factored form and use that sign chart to decide whether we're positive infinity or negative infinity. The overall limit will go, either does not exist, or if they happen to match, you can then use that symbol. Alrighty. So I'm going to run out of time if I jump into letter B. Letter B is a little bit more complicated because I think we're going to end up with a situation where something does cancel, but still gives us an asymptote. If you plug -3 into both of these, you will get 0 over 0, but we are going to end up with an asymptote. From there, on Friday, the only things we'll have to go over are these examples here, but we're going to use Desmos to help us with some of them. And our last example is going to be the same thing, but with a different question. And that different question is going to be identify the vertical asymptotes. So it's going to be your job to find out which limits make infinity and then say, hey, here's a vertical asymptote. But it ends up being mostly the same problem. You just have to write the limit. But you get those from the x pluses, x minuses. All right. Quiz tomorrow.